Hey everyone, this is Andrew. Welcome back to another episode in my SFML C++ tutorial series. Today I am going to look into adding a very basic physics system to my game, and the physics system is going to just handle the collision between circles and squares, which is pretty much all you need to get by. Doing anything more complicated is something I would consider adding, like if I ran to limitations of this current system. Before I start programming anything, I'm just going to open up Sublime. Holy cow. All right, so I have Sublime open here. It's just a text editor. I just want to go through like very roughly high level where I want all of my physics stuff to happen in my code. It's a really good idea before you start programming something to have a target in mind so you can actually know when you're done. But okay, anyway, so right now all of the things in our game, we have a player, we have an enemy, and we have an axe. Might as well just show the game real quick to see. This is where we left off last time. I haven't changed anything, so if you've been following along, you can, your game should look exactly like this. You click T, we go into this level editor mode where we put down these blocks. Okay, fantastic. Back to my Sublime document. So I want to add physics. So I think I'm going to add I'm just going to encapsulate everything in some sort of entity class. And then inside that entity class, I might have like some physics data, and then the physics data right now is you're either going to be a square or you're going to be a circle, and then you're either going to be static or dynamic. So static physics items will be items that never move, so we don't really need to run physics on them. They just are where they are. And dynamic items they do need to be simulated. So when they go through the state, they'll kind of be updated. I think that probably just a velocity is, a velocity is good to know that. And for the most part, we're just going to worry about instantaneous physics right now. So you either set a velocity or you don't. I'm not going to worry about forces or drag or momentum or mass, anything like that. The goal really is just to keep things from overlapping in the game world. The entity class itself will also just have a sprite, which is going to be sort of like just what our guys are right now. And then finally, I need to add a new sort of physics simulation function that processes all of the entities, and probably first we'd probably go through all the entities, and if it's a dynamic entity, we'll move it, and then we'll check if it collides with anything, and then if it does collide, we'll move it again to like resolve the collision. I think that if it stepping a little bit ahead, but if it collides with another dynamic object, then we'll want to move both objects. And yeah, I think I'm going to keep this sort of encapsulation. So yeah, let's just get started. I'm just going to move this over to the side, and I'm going to add a new class, and I'm just going to call this entity. And then we'll hop into the entity. I've been doing the def guards instead of pragma once because Clang tells me to. Sure. Don't need these, don't need that. That's all fine. Okay, it's not a virtual class. And we can have just trivial stuff right now. Okay, and then back to what I was saying, this is going to need to have some physics data. So I'm just going to define this struct inside of the entity. I'm just going to call it physics data. And I suppose I might as well say this now, but the goal with my tutorial series and what I've been talking about in my other videos is really to, as quickly as possible, without doing completely insane things, reach our goal on screen. And then in the future, we can always go back and restructure things if we want to. But I think it's overkill, especially when you're learning to start doing like these like advanced sort of like engine architectural ideas. Like I don't think it makes sense to make the physics data a component and then like have a pool for the components and iterate over the pool and have a whole physics engine. It's too much for what we want, and it'll take a lot of time to program, and the end result's going to be the exact same on screen. So anyways, back to this. There's a couple different I want to have a shape enum, circle and rectangle. Cool, good job. And then I want to have an enum for type. Wow, it's so spooky how good GitHub Copilot is, and it's like almost like they hear me. And then yeah, so the physics data will have a shape, have a type, and then I also want a velocity. So pretty close. I am going to include SFML system vector2. This is how we get the class SF vector to F, which is just 2 floating points. Oh, position. Yeah, that actually reminds me. One quick tangent here. I'm not actually going to keep track of the position in the physics data. I could. We'll keep track of the position. Sprites in SFML also have position inherently associated with them. And by having both a sprite position and a physics data position, we run the risk of them ever being out of sync. And we pretty much want them to always be in sync. So there's really no reason to have that be redundant. I'm actually going to comment this out right now. But maybe we want this in the future. Maybe we don't. We'll see. But okay, and the next thing I want to add is a SF sprite, and this is in the graphics library, or directory rather, SF sprite. Okay, very cool. We have like a super basic entity here, and now if we go back to our game and we look at our player, our axe, and our enemy, I'm going to just very quickly replace these with entities. So in the game, I'm now going to hash include, and I'll just include entity.h. And then instead of having a player, an enemy, and an axe, I'm going to have 3 entities. So that's I don't know what just happened here. Holy cow, I messed that up so bad. All right. We'll just have 3 entities. So our axe will be an entity, our player will be an entity, and the enemy will be an entity. Then if we go back and look at the entity, the sprite is private right now. And so we'll just add a, oh, yeah, we actually will need to do this also. We'll need to set the texture, set the scale, set the origin. GitHub Copilot literally makes programming just ridiculously easy. Okay, I'm getting distracted. So now we have, in our game, we changed everything over to an entity. And so we can't just say set texture. We need to say player dot, well, I guess we do say set texture, but just with a capital S now. And in this sprite, inside of the entity, we'll set the texture, scale, and origin. So we go back to our game, and we can just say set texture, set scale, set origin. We'll do the same thing here. Oh, set position. We need to add that one to our entity class. Let's do that real quick. Set position. And then we'll do set texture, set scale, set origin. And then I'm imagining, okay, yeah, move don't need to do this anymore. This will now be handled by our physics. So I'm actually going to write like a to-do to myself, which just says to-do, change this to be handled in physics. And then the same thing for the axe. Actually, the axe, it's maybe okay to do set position. Do we want physics on our axe? To be determined. I'm going to comment that out for now. Did the axe hit the enemy? This doesn't actually need to be done anymore. And then the enemy moving, this also to do. Change this to be handled by physics. Sure, that's fine. Okay, and then for drawing, we can actually do a nice little thing here. We can say our entity is a drawable, and then we need to implement the draw function. So draw, and then when you draw, we're just going to draw SF render target is not allowed. Oh, because I don't have that defined. Where is it defined? Render target is in graphics. So let's go just include that real quick. Oh, now it's happy. Okay, but if we, so when you include drawable and you define draw, that lets you just still call things directly from the window. So wherever in here we call draw, and we call draw enemy, player axe, or player and axe, it'll actually just draw the sprite that's inside of that class. What else do we have in here? I'm just gonna comment this all out. We don't need to do any of this nonsense now. I'm commenting it out instead of deleting it because I want to re-implement it using the physics system. But let's go through here, save. Really actually does not like that target.draw. Nope, not texture. Render target. Okay. Really? Okay. Yeah, it gives me an error, but it does compile, so I don't know why it's so unhappy. Moving on, so the physics data, there is some stuff we need to know about this. So if it's a circle, we need to have a radius. And if it's a rectangle, we need to have a width and a height. Do you want it to just be a vec2? No. I want it to be width and I want it to be height. If it's a vec2, I can't really name it width and height. It would just be a, width and height, and you just have to assume that x is width and y is height, and this is just explicit. No one needs to ask. It just is what it is. Okay. All right. I'm sorry. You can't make a mistake. Can't be misinterpreted. So we have these entities, shapes, blah, blah, blah. And the next thing we can do is let's actually just go into our game and we will add a function called update physics. Update physics. Very cool. And physics, wow, that was really loud. Update physics is, I'm just going to look at my little Sublime cheat sheet that I wrote down for me, is we need to iterate over all of the entities. And so just to keep this simple, what I'm going to do, note to self, I think, yeah. I am going to have a list of entities, and I'm just going to keep a list of like all entities. And this is every single entity in my game. And then we'll say for entity in all of my entities, if And then I need something to, actually for now, like why are we getting so crafty? Let's just say physics data. And we'll keep this public for now. We'll say, for my physics data, we'll say, okay, we'll go through all of the entities and we'll say if the entity is dynamic, we need to move it. And we will do that by saying entity dot move. Actually, this is not a bad way to do this. I really don't hate this. This is very reminiscent of like how we were already moving the sprites. And so I might as well just implement move in the entity and just move the underlying sprite. And then this also sort of plays into the idea that the position is not tied to the physics data. The position is gotten through the entity itself, and it's actually stored on the sprite. And I'll just go show you this right now. Like if we go to sprite, you'll see that sprite is a transformable, and the transformables have positions on them. They have positions, origin, scale. Holy cow. Here we go. Position of the object in the 2D world. So the fact that this already exists here, I think it's probably a good sign to just let that be the sole truth. Not to mention when we render the game, it'll always be true with physics, which is fine. You know, that's generally what you want. So I'm gonna say move, and it'll be with the velocity. Okay, and then now we need a couple things here. We need to do check for collisions for sure. And we also need to add a way for external sources to set the velocity. So I'm actually going to just say, yeah, this is fine. Whoops, void set velocity. And then we set the velocity here. And then in our game, before we were saying the requested movement was up here. Where does this come into play? Yes. Sorry, it's been I don't know if people probably watch these videos in succession, but it has been a moment since I have worked on this. It looks like we're getting the player movement. We're just adding all of these up. I figure we probably want to normalize this vector at the end of it, or else you'll end up moving slightly faster when you're moving along the diagonal. Let me go look. Does it get normalized anywhere? It does not get normalized anywhere. But thankfully, is this listening to me? It's so spooky. Okay, so we're just using our math helper that we set up like probably last episode or something to just normalize the vector and return it. So now our player movement is normalized. Does our normalized vector say length square root 0 divided by that? So if the length is 0, which is possible, this will actually fail. So what we want to do is check this case where we say if x is 0 and y is 0, just return the vector. It's not yeah, how do you normalize the 0 vector? That's a good question. We're just going to return the 0 vector and say, you do not get to normalize it today. Okay, so we have this player requested movement. And previously, we were just moving the sprite directly. And now what we're going to do here is we're going to say mPlayer dot set velocity. And we'll just set it to the player movement times the speed. And I'm also just going to change the name of this to say requested player movement direction. It's a little more specific, but direction typically implies that it's a normalized vector, and you'll have to multiply it by some speed to get an actual velocity. And then same thing with the ax here. I'm going to say, so the ax is just directly offset from the player. So maybe the ax should, okay. Yeah, we can just set the axis position directly. That's probably okay. And then we'll just make the ax static. So we'll say ax is player position plus this normalized vector plus this normalized vector. And to get the normalized vector, we need to uncomment this stuff, which is no problem. And then we don't need to set the position anymore. We do need to add get position, which is no problem. So let's go add get position now. We'll add it right after our set sf vector to f get position. There we go. Okay, go back in here. We're not going to worry about the axe hitting the enemy yet. It's a little overkill. And then for the enemy, we do want it to say find the direction to the player. But we don't want to call move. Instead, we want to say set velocity. Holy cow, I cannot type. Velocity. And we want to set it as this, but we don't actually need this delta time. No delta time. Times enemy speed. Enemy speed is undefined. There you go. Enemy speed. And then this velocity is just player speed. Cool. And then here we move it by moving velocity times delta time. And now if I save and compile, we get a couple errors. What did I just do? I don't know how that happened. Okay. Save and run. Nothing is moving. Oh, duh. Nothing is moving because we need to call update physics from somewhere. So we have, when we're running the game, we say update play. We set a bunch of velocities. When do we run update? We handle the input before that. Then we call update play. At the very end of update play, we'll say update physics. And then additionally, we need to account for all of the entities we've been adding. So when we add the player, the enemy, and the axe, we need to add it to our list of entities. So for now, we're just going to do that here. And we'll just say push back. Actually, just to be precise, I actually messed up a bit. These want to be pointers. We don't want to actually copy the entities. We just want to point to these local copies that we have. So we're going to push back a reference to the player. And then we'll push back reference to the enemy into the axe. And now when we run, we get, oh yes. These are pointers now. So it is physics data and move. Very cool. Oh, this is also pointer. Sad. Okay, it doesn't work. Let's see if we're actually hitting the update physics. Is dynamic. Duh. Okay. We need to, of course. Well, I suppose we don't necessarily need to check this. So this. Okay. So sometimes physics engines actually have 3 types of objects. They have static, dynamic, and kinematic. And kinematic is sort of like a static object that also moves. So it moves, but it doesn't really react to collisions. So right now, if we wanted to set up our axe to act as a moving static object, which it kind of can. Actually, no, I'm getting ahead of myself because we just set the axe's position directly. So it should be fine. I think all we need to do is make sure that the enemy and the player are set up as dynamic types. So what we're going to do is move our physics struct above our constructor. And we're going to say physics data type, physics type, and then here we're just going to say Physics data. Well, let's just go make a proper constructor for this. That's okay. So we'll add a constructor, and then we'll say our physics data dot eme type equals physics type. Nice. And now in our game, since we just put that as a required item in the constructor, we'll need to declare a physics type for all of our entities, which is no problem. We will say mPlayer, and we will say this is a dynamic item, and then the axe will be static. And we'll just, because we're just setting the axe's position directly. Excuse me. Okay. That's fine. So now we have more or less what we had before. Uh-oh. The enemy seems to move like extremely fast potentially. He's like already on top of the player right away. Where do we set its position to begin with? Enemy position is in the middle of the screen. What are we setting its velocity to? Enemy, oh, this would help. We need to normalize the vector to the player. So it's a direction. There we go. And now we more or less have the old system, except now we're moving with velocities, and we don't have any collision detection. So this axe does not work at all. And yeah, so let's do some collision detection now. So we need to say, okay, so we're a dynamic object, and we've just moved, and now we need to check for collisions. So we'll say, well, first let's see what this adds. So GitHub Copilot, let's see what you gave us. You said for every other entity, if it's us, yep. If it's itself, we skip it. Sure. If the length is less than 16, there's a collision. This is sort of okay, but what I'd really like to do is properly set up a collision check. And there's two types of collisions we need to worry about. Well, I guess three types. We need to worry about circle to circle, rectangle to rectangle, and then circle to rectangle. So let's do that right now. So, I am going to write a function, and it's going to be called process collision. And it's going to take in an entity, another entity, and then it's also going to take in a vector 2, and it's going to be called my resolution vector. Actually, I could just handle this internally in process collision. We don't have to worry about doing two steps. So I'm just going to have an internal function called process collision that does everything I need to do, including the resolution of the processing of the collision. So people might not like this, but I'm going to make this private, probably overkill, but, and I like keeping it close to the update physics so you know what it's all about. So we have an entity ref entity 1, 2. That's fine. We're going to go add a function for it. These are pointers, so we need to deref them. We're not going to worry about null pointers right now, but you know, you might need to worry about that at some point. So I am going to just hard code all of the cases right now because there's only 4, and once we're done, then we're done. So I'm going to say if entity1 dot get. Oh, I need to add a function to get the shape type. Get physics data type. Get type. Get shape type. Let's be more specific. Get physics shape type. Okay. If that's not what it is. Okay. If we're a circle, else if we're a rectangle. Okay, so that's pretty simple right now. We're a circle. We're a rectangle. Now we check the other entity. So we'll say if entity2 get physics shape is a circle, then we're both circles. If they're a rectangle, then we're a circle and they're a rectangle. We're going to do the same thing over here. So we say entity2, if they're a circle, then we're a rectangle and they're a circle, or we're both rectangles. And now we just need to add in the collision resolution for this. So the simplest case is we're both circles. Let's see if Copilot will do anything here. No. Okay. So what I'm going to do is SF vector to F, and I'm going to say entity 1 to 2. This is the distance, and then I'll add up our, let's see here, V entity 1 to entity 2 is minus the distance, and then float, I'm going to say sum of radii, which is, I probably should just add a get physics data function, which is fine. Are we ever going to modify any of these in the physics update? Velocity is not going to change because we don't care about that. Height, radius, type, we're actually not. It might be simplest to just add a get physics data. I feel like this could probably just be private then. That's probably fine. Does anything else yell at me? Well, yeah, this is gonna yell at me now, just for a second. But I can replace these with, I will say, get physics shape type. We will replace you with, oops. We will, holy cow, what did I just do? We will replace you with get physics data.me type. Okay. Happy there. All right, back to looking at the collision resolution. So when we're processing the collisions, if we're a circle and the other entity is a circle, it's not, this is the simplest case. What we're going to do is we're going to find the distance between, or I'm sorry, we're going to find the vector between the two positions, and then we're going to find the distance between the entities, which is the length of that vector. And these are all constant. And then we're going to find the sum of our radii, and if the distance between the entities is less than the sum of the radii, then we're colliding. And this has added a bunch of stuff here. I think we pretty much need none of this. Cool. So what we actually want to do is we want to say, so one guarantee that we have is when we, let me go replace these get physics data calls real quick. This is going to be get physics data, very cool. Okay. One thing that we can guarantee right now is that when we call process collisions, the first entity is always a dynamic entity, because we don't care about processing collisions for static things. We wouldn't be running this function and calling the entity there, because it's only for dynamic ones. But the second one could be static. So what we want to do is that if we're dynamic and we're bumping into a static object, only we'll move. But if we bump into a dynamic object, we both should move. So to do that, the first thing we need to do is just see if the other entity is dynamic. So just see if the other entity is dynamic. So we'll say is entity 2. Actually, we probably just if state this. Now let's just do this. Bool. Is entity 2 dynamic? We'll check that. And then we need to do our collision resolution. So it's not too bad. The first thing we're going to do is we're going to create, so this is entity 2's position minus entity 1's. So it's a vector that points from entity 1 to entity 2. So if the other entity is not dynamic, then we only need to move entity 1. So what we'll do is we'll just say entity 1 dot move, and what we need to move it by is the difference between the distance between our vectors. The amount we need to move it is the difference between the sum of our radii and the distance between us, and the direction that we want to move it is the direction from entity 1 to entity 2. I just said that backwards. We want to move it in the direction from entity 2 to entity 1. So let me see if my GitHub actually did this correctly. So it wants to normalize the vector from entity 1 to 2 and then use the negative value of that. That seems correct. And then the distance it wants to move it is the sum of the radii minus the distance between the entities, which is correct. That is correct completely. Else, we want to move both the entities. Let's see if it gave us a good one here. It's literally too good. So, and this is also correct. So in the second case, we want to move both of the entities. So what we do is we find that vector from 1 to 2. And we do the same thing where we multiply it by the sum of the radii minus the distance between the entities. But we want to move each entity half the distance. We don't want to move the full distance, or else when they collide, they'll jump apart and there'll be a space in between them. We want them, when the collision ends, for them to just perfectly touch still. And then we want to move entity 1 in the negative direction, and we want to move entity 2 in the positive direction. Okay, moving on to the second case here, where the first entity is a circle and the second one is a rectangle. I actually found this really cool website that explains how to do circle rectangle collisions very succinctly and with a nice visual at the top. So I'm going to, for the most part, skip over explaining it, but more or less what you end up doing is you draw, or you calculate a little triangle between the center of the circle and the closest edges of the rectangle. And then if the hypotenuse of that triangle is less than the radius of the circle, then you know that there's a collision. And it's a pretty elegant way of doing collision detection. I feel like none of this is obvious if you just think about it. But then once you see the answer, you're like, oh, duh. That's pretty straightforward. So we're going to let GitHub Copilot take the wheel here and see what it can fill in for me. And if it fills in nothing, we're just going to actually have to do what this website tells us to do, which shouldn't be too bad. Okay, Copilot is not playing along, so we're just going to do the collision test. Or rather, we're going to. Oh, what? Now it's starting to draw some stuff. What the heck is this? Closest X is clamp. We don't have clamp. That's okay. Clamp. Entity 1 position. Entity 2 position minus entity 2 position half width. And then. Oh, yeah. So it's clamping it between X and Y. I'm sorry. Between the left and right side. Oh. Yeah. Huh. Okay. Yeah, this is actually more or less doing exactly what the website is telling us to do, which is the first thing we do is we set test X and test Y to the center of the circle. And then we say if we're past the rectangle on the left side, clamp it to the left edge, and if we're past the rectangle on the right side, clamp it to the right edge, the X value, which is right here, this check. So if C of X is less than the right edge, set it to if it's less than the left edge, set it to the left edge. If it's greater than the right edge, set it to the right edge, else just let it be. And you can do that by clamping it. So I'm actually going to keep this, except the only thing we don't have is clamp. So thankfully the standard library has clamp, so we can just do standard clamp. And we're just going to have to hash include clamp. All right, to the internet for one moment. Standard clamp is in the algorithm header. So algorithm. Nice. Okay, now we have clamp. Okay, holy cow. I've just realized that we never mess with our C++ settings in the project view. So we're probably just default set to be using C++ 11, I'm assuming. And I would like to use, it's on C++ 14. I'm going to change it to C++ 20, and I'm going to change this for all configurations. I would not like to save what I have set so far. C++ 20, apply, okay. I don't know why you would be averse to using a newer version of C++. I suppose if you really don't want to use a new version of C++, be my guest, roll out your own clamp function. But for everybody else, you can just change it to C++ 20 in your project settings, and then you can say clamp, and it does what clamp does. So I'm just going to continue on with this tutorial. So we're going to clamp the Y value. So again, we're passing in the Y value of the center of the circle, and we're clamping it between the top and the bottom of the rectangle. I'm going to keep going down here. And this says, okay, that says closest. So I'm almost tempted to just see what GitHub Copilot fills in for me. Closest point. Circle to closest point. Is that what we want? Circle the closest point? Distance? Is it going to keep filling in things? If distance is less than radius, then we have collided. The second entity is not dynamic. Then we normalize the negative radius minus the distance. We need to move both entities. Is this just too good? Honestly, is this just too freaking good? Is this exactly what we need? Circle the closest point. This is exactly what it does. Minus that, minus that. Huh. Okay. So yeah, it has more or less just finished implementing this collision detection, which is fine. And okay. The second case is pretty much the same as the first case. or no, I'm sorry. This case down here, now we're the rectangle, and the other one's the circle. So it's pretty much this, but just flipped. Right? Pretty much just copy this, right? Yeah, except we're using entity 2, and we know entity 1 is the rectangle. Then we'll say this is the closest point. It's the length. And then here is the distance is less than entity 2's radius. And then the only difference here is that we're defaulting to moving entity 1, but we need to say it still needs to be the same as the top. It can't be flipped around. So we need to say, is entity 2 dynamic? If entity 2 is not dynamic, then we only need to move entity 1, and we'll move entity 1 by this positive value now because we've done everything backwards. Sorry, that might be a little bit completely ridiculously confusing, but and then else they're both dynamic entities, so we need to move both of them. So we'll say entity 2 to 1 to 2 to 1. Okay, cool. And then this is the case where they're both rectangles, and rectangle collision is also pretty simple. The overlap. Okay. Just to show you what's going on here, I'm going to quickly sketch it in Paint. So if we look at these lines of code it's drawn out for us, let's say we have two rectangles. I will draw some basic shapes real quick. Rectangle 1, and we have rectangle 2, and the rectangles have some center point, and they have some width, and they have some height. The first thing that we do is we measure the distance, just the x distance, between these two center points, which is right here. And this is this first value up top. And then we measure the overlap, and the overlap is the sum of the widths, or I suppose half widths, minus this center, or this like central distance between the rectangles. And so you can see here that because the rectangles aren't touching, when you add this half width and this half width together and you subtract this middle half width, you'll end up with a negative value, and the negative value will be equal to the distance between these rectangles here. So just that alone, if this f overlap x is negative, there is definitely no overlap because there's a gap between the rectangles. And then what we essentially do is we do the exact same calculation, but with the heights. So we measure this half height and this half height, and then we measure the distance between these two, and we subtract them. And in this case, you'll actually end up with a positive value, and that positive value will be the distance here. Now, this means this means that there could be a collision, but there isn't, because, you know, this value ended up being negative, that distance, the x distance. But when both of them are positive, that means there's definitely an overlap, which is all this is doing, which is pretty it's very simple, but it works. And because GitHub Copilot just does it for us, we don't have to look this up online. So yeah, what the heck? Keeps just putting in true. It's not what I want at all. Tab to accept. tab to accept. Okay. So let's just check this out here. So if X overlaps and Y overlaps, we are guaranteed a collision. If it overlaps more in the Y value than it does in the X value, what this is saying is move both of the entities some half overlap value, and this one is doing the opposite. But like I said earlier, we don't ever want to move the second entity if it's a static entity. Or I'm sorry, we only want to move the second entity if it's dynamic. I mean, that's more or less saying the same thing. So say, is entity 2 dynamic? Here, or in here rather, we'll say if entity 2 is dynamic, then we do exactly what it says here, which is entity 2 is dynamic, so we want to move both of the objects. Else we just want to move the first object, and then we want to do the same thing in the other direction. So if entity 2 is dynamic, we move both of these. Else we just move one of them. And you'll notice that when we move both of them, we move them by half amounts, and we just move one, we move it by the full amount. And these are if it overlaps more in the X direction. We'll do the same thing for the Y direction. So if this overlaps like that, is that all correct? Entity 2, if it's dynamic, yep. Move half plus half, yep. Okay, and then here we'll say something similar here. Nice. And I know what you're thinking is that, hey, you didn't actually program any of this. I didn't see you type anything. GitHub Copilot typed all of it. Isn't that cheating? And it's not, because all I was going to do before was go online and copy code. So this sort of just cuts out the middleman and just writes the code directly in the IDE. It's mega convenient. And just a spoiler alert, as you program more stuff, GitHub Copilot becomes less useful. But this very basic, like rudimentary tasks that you can just look up online and people will give you pretty quick answers to. It's pretty much stellar for doing all of that. And then the last thing that we're going to need to do is we're going to need to set up the width and height of our entities. And I'm sort of inclined, where is my entity.h? I'm sort of inclined to also make the width and height just directly get ripped out of the sprite since it has a transformable with it. The radius could essentially just be half the sprite's width, and then the width and the height, those are genuine properties of a sprite. I'm sort of tempted to do that. I'm not sure what's stopping me. Let me think about it for a sec. Okay, I have thought about it, and I've decided to keep it how it is for now. I'm just going to add 2 helper functions. One helper function to set up the entity as a circle, and one helper function to set up the entity as a rectangle. And then we can sort of just make sure that we pass in all of the relevant information for that. So I'll say set circle, which takes in a radius, and it'll set the shape type to circle and set the radius to radius. And then I'll also have set rectangle, which does something similar, but for rectangles. And then in my game for the enemy, I can go enemy.set circle physics and its radius. And the enemy's radius will be 80 because it's a 16 by 16 sprite, and we've scaled it up tenfold. So all the way across it would be 160. So radius is just half of that. We'll do the same thing for the player. We'll set the player's physics to 80, and we'll also do the same thing for the axe. Okay, and then let's see if this runs. Nice. So we've got the player and the axe here. Everything seems to be working normal. Seems to be some amount of physics, but it looks a little off. Oh, I think I have the radius. Maybe the radius should be 160, actually. I suppose I don't really know why it should be 160. Oh. Okay. Wow. So if you've been following along, I have been writing down type here for a lot of the wrong types. So if we go back to here, this is an enum, this is an enum. I believe we can make these enum classes, and what that will do is the compiler should yell at us whenever we misuse it. Okay, and now it pops up. So highly recommend using enum class when you don't want to mix up the use of your enums. Let's see here. Has no member dynamic because it is type dynamic. Okay. Yeah, and this is just much cleaner. So thanks C++. And here we'll say update the physics if the physics type is that. And here, this is just completely wrong. It's not type. We're looking to check the shape. So we'll go to shape. Is that? And same with here. This is supposed to be checking the shape. Whoops. The shape. Here, this is actually supposed to be checking the type. That's correct. And another shape one here. And you'll see this is an error now. You can't compare type to shape because they're not the same enum, which is good. That's exactly what we want to happen. This is a type. That's a type. That's a shape. That's a type. Yep. Shape. Shape. Which means these need to be shapes. Makes you wonder how anything was working before, but we'll just ignore that. Code just runs if you tell it to. So that's undefined behavior. ME shape. And I wrote ME shape here. Holy cow. Shape. I think that's all of them. So we're going to build again. Still not happy. Like, okay, fine. Yep. This needs to be everywhere now. No loose ends. Build again. Okay, let's check this out. I don't need a breakpoint here anymore. Okay, so this is kind of funny. So immediately, I couldn't actually move to the right because I was running into my axe. So now my axe genuinely hits this guy pretty good. It seems like physics is working. If I just hands up, the guy moves me and I can smack him away. Yeah, so this is mostly working. I think the next step would be to add some sort of like ignore collision between two entities. And here you see the static entity working its magic. So the skull is trying to move into the axe, but the axe is not moving because the axe is static. Actually, let's add that real quick in our entity in the physics data. We'll just add a standard vector. Holy moly. Standard vector of standard vector of entities, and we'll say ignore me. No, that's a silly name. We'll call it what it is. Entities to ignore and we need to include vector up top. And then now we can do something like this. Well, here, we'll say, we'll add a little helper function first, which is add entity to ignore. And then in our game, for our player, we'll say mPlayer, add entity to ignore, and it'll be the axe. And then once again, we actually want to take in pointers here. We don't want to be copying these things. So this is entities to ignore, and then in game, we want to pass in the address there. And then when we update our physics and we're looking for entities to collide with, we can say if entity dot should ignore, let's see here, actually we should add just another little helper function here, and we'll say void, or boolean rather, should ignore entity for physics. Takes in that entity, we iterate through all of our entities to ignore, and if it's in that list, we'll return true. If not, we'll return false. And then here we can say if should, that's a pointer, should ignore entity for physics, and we pass in the other entity. If we should ignore them, then we'll just continue, else keep processing. And now when we run this, we should be able to just move right into our axe. Yep, so now when the player moves, it just doesn't even pay attention to the axe, and we can go up and just, beat this guy up. And it's all physics-y. The last thing I want to add, just as a little icing on the cake before we get out of here and to test out some of the rectangle collision, is to just change our tiles in our game to also be entities. So let's do that. And they'll be rectangles, obviously. So we'll say, well, tile options is probably fine to leave as that, but for the actual tiles, we'll change that to entity. Sure, no problem. And then let's go and look for all of the uses here. So now this will be for tile and tiles. Yeah, so now we'll say for const entity in, not all entities, in tiles. Of course, because this is a reference. These are real entities that we're storing in this list, not pointers. We'll draw all the tiles, no problem there. And then let's go to this one. So we create tile at position, check if there's already a tile at the position. So now we say get position equals this tile's position. If there is, delete that tile and then push back tile, but we don't want to push back tile. What we actually want to push back is an entity, and it will be a static entity, and I'm just going to call it new tile, and we can actually say in place back, and we can just pass this in directly here, and then this will return an entity. So I can just say new tile equals and place back. And then we want to set up the rectangle. So we'll say set up rectangle physics, and our tiles are just 160 by 160. That's the height and width. So no problem there. And then they have the position set, but they do not have an origin. So we don't do the origin offset, which is maybe fine. Maybe. Is it okay, actually? Oh, look at that. We do x times that plus 80 when we draw it. When we draw, Okay. We'll see how this goes. Then we go delete tile at position. How does this go? If position equals that, back, pop back. Sure. And then when we process the physics, it's update physics. We'll also need to update or iterate through all of the tiles. So we need to iterate through all of the entities, and then we need to iterate through all of these entities. And additionally, so how do we want to do this exactly? Okay, we were missing just a few things. So before we were just copying over the sprite information for the tiles when we created a new sprite directly, and we lost that functionality when we made an entity class. So the next thing we need to do, or just to get us back to the old functionality, is to add a set sprite function, which just takes in a sprite and sets it directly on our sprite, which just does a copy of the sprite. And now we can do something very similar to what we were doing before. So we can just say right here, after we add the new tile as an entity, we can say set sprite, and we will set it to the tile that is selected in our tile options, and then we'll set up the rectangle. Okay, I always forget that storing pointers to all entities is dangerous when those entities live in other vectors, because as the vector grows, if you were pointing into a spot in the vector, it might not necessarily be the same spot in the new vector after it grows. So keeping a list of tiles is fine, but keeping a list of entities like this is not fine. And there's probably, well, here, I'm actually going to copy just this bit. There's probably better ways to do this, but since we're at the very tail end of finishing up this like very basic physics system, we're going to do this the way that I know will work, but you'll see that it's obviously a little bit of redundant work, and that is just when we go to update physics, we're just going to have a local list just that exists within this physics update, and we're going to add all the entities right here, do it on the fly. So we know that we need to add the player, we need to add the enemy, the axe, and then we'll need to add all the tiles. So for all the tiles, we'll add them to the entities list, and then we're just going to iterate over this list, this local list, so we know it's fresh. And then I'm going to delete where we were adding to the old list, and we'll run this again. Okay. And now you'll see that we have some tiles in the world, and the player can't move past it, and neither can the enemy. And the enemy is just sort of crawling towards us. And if we were to run around to the other side of the tile, we could probably get them stuck, because the enemy is very dumb and he just tries to run in a straight line to us. So I think he'll get stuck here right now. Should be stuck. And yeah, that's basically it. This is a very basic physics system. It gets the job done. And honestly, I would try not to worry too much about the complexity, or I would err on the side of making a less complex system that works than making a complex system that's supposed to be very performant, especially when we're learning, and especially when we're making a game that's this simple and small. So thanks so much for watching. I really appreciate it. I hope you learned something. I definitely learned something making this video, and I'll see you in the next one. Oh, and one last thing, just like always, I will post all of this code on GitHub. And if you're on the GitHub and you look through the change list, you'll see all of the changes that were just made for or related to this video.